ಮೈಕ್ ಅದು ಚಾರ್ಜ್ ಐತಿ ಇದು ಚಾರ್ಜ್ ಐತಾ ಚಾರ್ಜ್ ಇಟ್ಟಿದ್ದು ತೊಗೊಂಡೆ Good morning. So in the last class we have discussed about the dimensioning, type of dimensioning and tolerance. Tolerance is nothing but the upper limit minus lower limit and why we need to provide tolerance for the dimensions. So these all things we have discussed. So in today's class we will proceed further with the material conditions. The material conditions. So there are actually two types of material conditions. One is maximum material conditions and we call it as MMC, and lower material conditions or lower material condition or minimum material condition. One and the same. Minimum material condition we call it as LMC. We call it as LMC. MMC and LMC. Just remember that. So when parts are called for assembly, we categorize the parts into basically two types, that is holes and shafts. Basically into two types, that is holes and shafts. Let us consider first the shaft. Let us consider first the shaft. Let us this be the shaft and this be the tolerance on the shaft. This be the tolerance on the shaft and let this be the lower limit and let this be the upper limit. So I'll assume this dimension as dia 50 and this as dia 50.02. That means what is the tolerance on this shaft? That is upper limit minus lower limit, that is 50.02 minus 50, hence the tolerance is 0.02 mm. Now what is the maximum material condition for this and lower material condition for this? What is the maximum material condition for this and lower material condition for this? Now, so maximum material condition for the shaft is that condition when the shaft is having maximum material. So when the shaft is having maximum material, when the shaft is finished to upper limit. So the amount in the shaft is maximum, but when the amount of material in the shaft will be minimum when the shaft is finished to the lower material condition, the amount of shaft material in the shaft is minimum, hence maximum material condition for the shaft is upper limit, while the lower material condition for the shaft is lower limit. So here in this case it is 50.02 and here it is 50. Now coming back to hole. So this is the dimension of the hole on a square plate. Now what is the maximum material condition and lower material condition for the hole of dimension 50 plus 002 plus 002. Now the condition is that for the maximum material condition, it defines the condition for the limit when the amount of material left in the shaft is amount of material left in the square plate is maximum, and lower metal condition is that condition, or the lower metal condition is the condition which corresponds to the limit which signifies the less amount of material on the square plate. Now when the shaft is here, in this case upper limit is how much? It is 50.02 and lower limit is 50. I just draw a diagram of this over here again, just a rough diagram. Just to elaborate these two, I am just drawing a difference in the dimensions of the hole. Let us assume that this dimension is, it is 50.02, and let us assume this dimension as 50, because 50 is always less than 50.02. Just to discriminate, I have drawn this hole a slightly smaller than this, just for easy comparison. That is not one-to-one dimension. Okay. Now I told you that maximum material condition is that condition, or is corresponding to the limit which states that the amount of material left in the square plate is maximum. So this is the amount of material left in this square plate, and this is the amount of material left in this square plate. So in either 1 or 2, in which condition the amount of material left in the square plate is maximum? In the second case, which corresponds to the lower limit, hence that will become the maximum material condition for the hole. And the lower material condition, or the minimum material condition, is that condition with respect to the limit the amount of material left in the square plate is minimum. So in this case, when the amount of material left in the square plate is minimum, when the hole is finished to maximum, that is when the hole is finished to upper limit, that will become the lower material condition. So is that clear? This will be again 50 and this will be 50.02. So it is vice versa of the shaft. And also we have discussed the geometrical dimensioning and tolerance. Why we require geometrical dimensioning and tolerance? Because if you want to control the feature of any part, then we need to specify this geometrical dimensioning and tolerance. So basically we have discussed the form tolerances. Basically there are four types of form tolerances. There are four. One is the straightness, flatness, circularity and cylindricity. Straightness, flatness, circularity and cylindricity. Straightness we have discussed. Why we use straightness symbol? Because if you want to control a line or an edge of any part by a dash or a flat line, we'll discuss it further. And flatness, why use flatness? If you want to control the plane of any surface of a part, we use flatness. And circularity, if you want to control any circular feature of any circular part, we use circularity. If you want to control the cylindricity of any circular feature of a part, we use cylindricity. This is how we are going to use it. I have told it in the last class itself that this is a symbol and this is used to control this edge, which has to be a straight line, and if it is not possible for us to achieve this straight line, and the deviation must be well within 0.030. That is what it is stated over here. So this is how it looks like. That means if the edge of that part is not being manufactured perfectly straight, then there will be certain variation, what you can see here, but this variation must be well within 0.030, which is specified by this two straight lines, which is called as the tolerance zone. This all we have discussed, and again I am just going through this very fastly, all these four tolerance symbols. Then the second one is the flatness, and the flatness, again I told you in the last class itself, it is used to control the surface of any part, and here again I want to control this surface, and then I have used this surface, I have represented by an arrow line, and on the base of the arrow line I use the symbol of what we need to control, and this is the flatness symbol. And again after that we need to mention a tolerance in one more block, that is the tolerance mentioned over here is 0.030, and this is how. As far as the straightness was concerned, if you look at carefully, the tolerance zones were specified by using two parallel lines, but here the tolerance zones is specified by using two parallel planes, because here we are going to control the tolerance of a plane or a surface, hence the entire plane and the surface has to be covered by the planes, hence the tolerance of this tolerance zone of the flatness is controlled by using two parallel planes. So similar, this example also we have discussed, and with respect to coming back to the circularity, again this is a circular part, and if I want to control the circle of this part, and this is indicated by arrow line and accompanied by the symbol, what we use here, it is a circle, and the tolerance zone that is specified is 0.030 here. And similarly here, the circularity tolerance zone is specified by two concentric circles. The circularity is specified between two concentric circles. We know that when the part has to be manufactured, it is not possible to produce a perfect circle, hence there will be certain variations, but hence there will be certain variations, which is indicated by a red line over here, the arrow is also indicating, but this variation has to be well within the specified concentric circles that represent the tolerance zone. And cylindricity. A cylindricity, again we have discussed, it is represented by this symbol and followed by the tolerance. This is a symbol, that is a circle with two parallel tangents, and here the cylindricity tolerance zone is specified by using two concentric cylinders. So here it is not possible for us to always produce a perfect cylindrical surface, hence there will be certain variation which is represented over here. If you look at over in 3D, this will be the variation which is represented by the red line. and the two concentric cylinders, one above and one below, represents the tolerance zone, and the part has to be manufactured well within this tolerance zone, then only it is accepted or else it is rejected. The next type of symbols are the orientation symbols, that are parallelism and as the name itself suggests, that parallelism is used to control the parallelity between the two surfaces and the perpendicularity. As the name itself suggests, it is used to control the perpendicularity of the surfaces, and angularity, as the name itself suggests, it is used to control the angle between the two surfaces which are inclined to each other. So, discuss the symbol here. The parallelism, what you are looking over here, this surface we want to be parallel, but this surface has to be parallel with some other surface. So, parallel means one surface has to be parallel with another surface, hence here it is indicated. Just look at the feature frame over here. So, this surface is what we need to have parallel, hence the arrow is representing this surface, and the parallelism symbol, that is represented by two parallel dashed lines, that is over here, and then followed by the tolerance, that is 0.030, but there is mentioned something called as A after that. But previously in the form tolerances only the dimension symbol block and followed by the tolerance block were mentioned, but over here in case of orientation symbol we are using three blocks, one block for the symbol and one block for the tolerance specification and another block for the datum specification, So here this parallelism means we want this surface parallel to this surface, because this surface I have made as a datum A. This surface I have made as a datum A. Hence, this surface has to be parallel with this surface. That is what it is indicated over here with a tolerance of within a tolerance of 0.030. Here. Again, the tolerance zone over here is specified by two parallel planes. The tolerance zone is again specified by two parallel planes. So here, considering this example, this surface I have made it a reference surface and I taken it as a datum A, which is represented in a 3D on the right side, and on the left side the top surface, what as indicated in the diagram, has to be parallel with this surface within a tolerance zone of 0.030, that is depicted in the right figure. That means this I have taken as a reference plane which is completely straight, and this surface has to be in the parallel with this within a tolerance of 0.030, and this surface tolerance zone is represented by two parallel planes which are separated by 0.030. And again the parallelism is indicated by measured by making the gauge running through the entire surface, and is deviation within the 0.030, it is accepted or else it is rejected. This is how the measurement is made after the manufacturing of the part. Again, here if you look at the gauge, this gear profile needs to be parallel with this, needs to be parallel with this, needs to be parallel with this, and again this gear profile, this tooth, this side of the tooth has to be parallel with this side of the tooth and has to be parallel with this side of the tooth for the proper gear geometry. Hence that is indicated over, that is also indicated, but again what they are indicated, this was the gear with the tooth and this surface and this surface, this were the tooth, this is a gear profile and there will be tooth on this, and this surface and this surface they want parallelism, and that parallelism is indicated over here, that this surface and this surface, that is this top surface and again that bottom surface needs to be parallel, because the bottom surface they have taken it as datum A and the top surface they want to be manufactured with respect to datum A and within the parallel of 0.1. So that is how it is represented over here. And next is the perpendicularity. So for all this we require datums. For parallelism, perpendicularity and angularity we require datums. Use of the datum, that means we require 3 blocks in a feature frame. Now over here, perpendicularity. Perpendicularity, and this is the part we have taken to demonstrate this perpendicularity. I want this surface to be perpendicular with a tolerance of 0.030 by taking with a reference of surface A. The surface A, what I am taking reference is nothing but, we need to represent in the diagram as datum. Hence, that is this surface, and this surface are represented as datum. That means this surface has to be perpendicular with this surface. If it has not to be perpendicular, then the variation must be within 0.030. Perpendicularity means what? This surface has to be 90 degree with this surface. If it is not possible us to achieve 90 degree, then the variation must be within 90 plus 0.030 or minus 0.030. Oh, sorry, 90 plus or minus 0.030. And this perpendicularity can also be used for the axis of the hole. Now, this is better demonstrated by using this diagram. But one more condition what they have used is, that is, they have used the symbol perpendicularity and followed for the axis they are shown as the diameter or with a tolerance of 0.030, and something they have told, that is M circle that represents the maximum material conditions for the hole. What will be the maximum material condition for the hole? When the hole is finished to lower limit, and again followed by the reference surface. They are taken it as datum A, and which is indicated as the bottom surface of this square plate. That means this axis or this axis in the side view has to be in perpendicular to this bottom surface with the maximum material condition and tolerance of 0.030. That is what it is depicted in this feature frame. And one, this tolerance zone again is represented by 2 parallel planes, that is represented over here, and this is the datum. What is the perpendicularity variation? It has to be within these 2 parallel planes, and this is with respect to the axis. If the axis is not perpendicular, this is what it is going to result in. And again the surface, perpendicularity for the axis, angularity. You can see a part, and this surface is slightly in angle, so I want this control this inclination. Hence I am using the arrow to represent this surface, and the symbol what I am using for the angularity is like this, followed by a tolerance of 0.030 with reference to datum A. The datum A is the bottom surface. Hence, with respect to this bottom surface, with respect to certain angle, it is mentioned 60 degree. If this 60 degree is not possible for us to achieve, there will be a slight variation, and this variation has to be 0.030 with respect to A, because I have taken the reference as A. That is what it is depicted in this feature frame. So here the same thing is shown with respect to the tolerance zones. Again, the tolerance zone is represented by 2 parallel planes, that is 2 parallel planes over here. The 60 degree is marked, and before 60 degree and after 60 degree we have made a plane, 2 parallel planes, which indicates the tolerance zone of 0.030. So this is how it is measured, by using gauge, by using the sand principle. That means we need to make that surface parallel, and then we need to measure the variation by making the gauge to run on this entire surface. If the variation is exceeds 0.030, then the part is rejected. If the variation is well within 0.030, then the part is accepted. Sorry. So here these are the different parts where the angularity symbols can be used. You can just have a look. And the next set of tolerances are the location tolerances. The next set of the tolerances are the location tolerance. And among that, first one is the true position, the second one is the concentricity, and the third one is the symmetricity. And again, there is one more, it is just a modification of this, hence we will not stress much on this. The basic tolerance symbols we are going to stress in the location type of GD&T symbols. Among that, the first one is the true position, and the second one is the concentricity, and the third one is the symmetry. So as you can predict by the name itself, true position means it specifies with respect to the position. But here in this case, we are dealing with the position of the center point of the hole. Position of the center point of the hole. If a part has a hole may be any kind. It may be a true hole, blind hole, or up to different types of holes. But there has to be an axis with respect to that hole, isn't it? While manufacturing, if the axis shifts, or the axis must be on the top surface, it will be the center point. If the center point shifts, then what must be the tolerance that must be accepted if the shift happens? That is indicated by the true position. Concentricity. Concentricity is used when the part is having like a contour bore holes with the same center axis, or a stepped shaft. If you want to control the second step of a shaft with respect to the first step of the shaft with respect to certain tolerance, then we are going to use this concentricity symbol. And next is the symmetry. When the part is having symmetry, then we are going to choose the central axis, and we are just going to make a dimension with respect to the tolerance to only 1/2, and then with respect to the central axis, we are going to use this symmetry symbol to highlight that the other part, which is a mirror image of the first side, must follow all the dimensions and tolerance what have followed for the other half. That is, so this is the examples I am going to consider to explain or to illustrate the true position in much detail. So this is a square part wherein there is a hole. The axis of the hole from the bottom is 30, and from the extreme right corner it is 20, and this is the datum A, reference surface A, and this is the datum B, that is the reference surface B, and the position tolerance for this is given as the position symbol followed by the diameter of 0.030 with respect to A and B. With respect to A and B, because the central axis dimension is given from this surface, bottom surface, hence I am taking this as the datum A, and from the right surface also they have given the central axis symbol, that is this surface, hence I am taking it as point B, because the coordinates of the point in x has to be mentioned in xy direction, hence they are mentioned in two directions, and those two surfaces I have taken that as a reference plane as A and B, or datums as A and B. So now, actually the blue hole is what it is desired, and blue center point is what it is desired, but in manufacturing what happens is that there will be slight shift, because it is not possible to manufacture well within this at all the time. The central hole has to be finished at this point only with respect to this center point that is indicated by blue. There will be a certain variations, hence the variations, what is the maximum permissible variation is indicated by or is mentioned by this true position. See here in the part actual processed part where it is indicated by red, this is a red hole that is actually being finished, but blue hole is what it is desired on the part, and blue point is the center point of the hole, that what is desired, and the red point is what we got in manufacturing, there is a certain deviation from the blue to red, isn't it? There is a certain deviation in the blue to red. So this deviation, if the deviation is well within 0.030, then the part is accepted. If the deviation is more than 0.030, then the part is rejected. See here, with respect to x and y also we have shown the blue hole, and with the center point I represented with respect to x, and with the y, that is the true x and true y what we desire. But what we get in actual is true actual x and actual y. So this is how the formula is compared with respect to the true position. That is actual x minus true x the square plus actual y minus true y the square and the square root of this. Concentricity. Coming back to the concentricity, as I told, the concentricity is mainly used for the stepped shafts. So here it is a stepped shaft, two-step shaft what is taken for an example. This is the step shaft of maximum diameter, and this is a step shaft of the minimum diameter with respect to these two diameters, and I want to control the diameter of this shaft and with respect to the diameter of this shaft. That means I want this diameter of this step with respect to this step, that means from the same axis. So that is what it is represented. Suppose you consider this as a circle and this as one more circle. This circle and this circle must have same axis or same center point. That means this stepped part and this stepped part must have same axis. So that is what I need to control by indicating, that is this feature that is indicated by this dotted lines, and by symbol, concentric symbols, that is one circle after another circle, and then the diameter of 0.030. That means if this step diameter is having 50 mm and this step has to be finished with this tolerance of 0.030 from data main. See here, as I told, it is with respect to the axis, hence for the axis they have represented the tolerance zone. So this is the datum axis, that is for the previous step, and this is the axis of the second step, and the axis of this second step I will need to control with the first step. Hence there will be slight variations, and this variation has to be within this tolerance zone, which is indicated by the parallel lines. The difference between these two parallel lines is nothing but the tolerance that is specified on the diagram, that is 0.030. And again, the concentricity is measured by moving the gauge, and if the variation is well within the tolerance zone, it is accepted. If the variation is above the tolerance zone, the part is rejected. And here there is one more example which depicts the concentricity. Just go through this. Now symmetry. Now consider this part. If you look at this part very carefully, what I can see is that if I use a central axis for this part, this half, if I mirror image, then this half will be exactly the same of this. That means this half is the mirror image of this part. This half of the part is the mirror image of this half of the part. Then the axis bifurcates that mirror image dimensions. So if I give this dimensions, and this dimensions, and this dimensions with the required tolerance, and for this part I need to give tolerances, but instead that what I'm going to use, I'm going to use a symmetry symbols. I'm going to use a symmetry symbol followed by what tolerance these features or this dimension has to be controlled with respect to this dimensions, that is 0.030 with respect to datum A. That is what symmetry is used. See here, or you can see better representation over here. Again, the example, you can just have a look at this. The axis, this axis is controlled, these surfaces are controlled, that is represented by this. Okay. And then the last set of GD&T symbols are the runout and profile features. Runout and profile symbols. Runout. Runout means it is again used for the circular feature itself, which are having concentricity. This is the step, the first step, and this is the second step. I am using a runout symbol as this, and tolerance as 0.03 with respect to reference A. What does it indicate is that if it is having two shafts, look closely over here, it is very small. This is one step diameter and this is other step diameter. These dimensions are mentioned, and this is what the runout I need to control. Runout means if I place a gauge and if I rotate the part by 360 degree, and what is the variation that I am going to get? What is the variation I am going to get? So this variation has to be the within 0.030 with respect to this. So I'll repeat it one more time. This represents this diameter, this represents this diameter, this represents this diameter, this represents this diameter. The runout means if I place a gauge and if I rotate the part by 360 degree, then the variation in the gauge must be well within 0.030 in diameter compared to this. See here, that is what it is showed over here. So this is the second step, and this is the first step. If the variation is this variation, this is the actual red line, what is indicated, it is like this. This red line is nothing but this actual manufactured part. This black line is this part, and blue line, these two concentric circles, what you are seeing by blue lines are the tolerance zones, which are specified with respect to this red manufactured line. So this difference between these two lines must be well within 0.03. That is again here, this is this part, this is this feature, and this blue lines are indicated the tolerance zones. See here, the measurement is done by gauge and rotating the part by 360 degrees. And this is how it is shown over here. So you can very easily it is depicted. So this is the first shaft, it is rotated by 360 degrees, and this second shaft, it has to be manufactured with the runout with respect to this. And if you place the gauge and if you rotate by 360 degrees, and this will be the variations, what you can see the variations. These variations will be must be well within 0.030. Earlier when it has touched, there is no variation. When it has moved to 360 degrees, you can see the difference by over here, and this difference must be well within 0.030. That is what it is indicated in this particular drawing. And the symbol used is this. And now coming back to the total runout. Total runout is represented by a symbol like this. Two arrows connected, then the bottoms are connected. And next the tolerance is specified, and one datum is required to use the total runout. Again, there is a modification of the runout. It is the modification of the runout symbol. Again, it is used for two step diameters. So this is the first step diameter, and this is the second step diameter, which is comparatively less than this. And this step diameter we have taken as the datum. See here. So earlier case, what was the case in the runout? In the runout, if this was the first step diameter, which was the maximum, and this is the second step diameter, which we need to control with respect to this. The runout is that when we place this and when we rotate it, the tolerance specified must be well within that. But here in the total runout, what happens is that I am not only rotating the part by 360 degrees, but I am moving the part linearly while measuring, either this side or this side. Because of which what happens, the entire cylinder surface of the second step is covered. It is typically, if I compare this with runout and total runout, I can compare with runout with circularity and total runout with the cylindricity. I hope now you people have got the point. See here, it is not only rotating, I am not only measuring by keeping the gauge and just rotating the part, but I am also moving the gauge linearly, because of which it is indicated by over, because of which I am going to get not only the profile of a circle at a particular point, but entire cylinder. If you want to control the entire cylinder variation with respect to the first step diameter, then a total runout needs to be called out, or total runout has to be represented in the feature frame. See here, that is what it is represented in this diagram. So for the particular drawing, this is the first step diameter and this is the second step diameter, and I have called a total runout of 0.2 with respect to datum A. So if you look at the side view, it will be first step and this is the second step and this is the central axis and this is the variations. Now here you can see the variations. So this is the first step, this is the second step. Once the variation 0, and now I am not only rotating the part, I am not only rotating the part in linearly. So because of which the major lines are this one, this one, this one. It will be like this spiral until and unless entire length of the part is step is covered. And after that, if you can see, variation has to be well within 0.030. Next, profile of a line. Profile of a line. So this profile of a line, it is with respect to the surfaces of any part which are not true surfaces. Like it basically a curved surfaces. For the curved surface, we are using a profile of a line and a profile of a surface. Now this is the profile of a line and it is mentioned in the diagram. And this profile of a line has to be, if the symbol is used this, and the tolerance is 0.030. With respect to two datums, it needs to be represented with respect to this surface as well as this surface. That is datum B and datum A, which is represented by A and B. So this is how it is looks like. So for this surface, I have measured this surface or this profile I need to maintain, that is this profile I need to maintain, that is this profile I need to maintain within a tolerance zone of 0.030, which are separated by a tolerance zone of 0.030. So again it is measured by moving the gauge on the surface. If the variation is well within that, then it is accepted, or else it is rejected. And next is a profile of a surface. That thing was only profile of a line on a particular line. But if you want to control the entire surface, so again this I am going to represent or have a similarity with straightness and flatness. What happens in straightness? We are going to control only a line or edge. What happens in flatness? We are going to control an entire plane or a surface. Similarly over here, in profile of a line, we are going to control only a line on the curved surface. In a profile of a surface, we are going to control the entire curved surface. That is the difference. Again, the surface is same, but only the symbol is changed. Instead of line, it is covered by a surface. Instead of line, if you close this, it will become a surface symbol, and the tolerance is represented by 0.030 with reference to the same, that is this surface and this surface, that is A and B. So this is how it looks like. This is how it looks like. But it is represented by not only the lines but by the planes, the tolerance. And this is how the measurement is carried out on any surface. Now can you just do this? Match the following geometric tolerance type with appropriate tolerance category. Flatness, which type among the right side? Perpendicularity, symmetry, profile of a surface, total runout. It is like this. Flatness is for the form tolerance. Perpendicularity is again the orientation tolerance, that is the second type. Symmetry is for the third type, that is the location tolerance. Profile of a surface is the profile tolerance. Total runout is the runout tolerances. Now, we look at the figure very closely. We look the diagram very closely. There are certain dimensions, there are certain tolerances, there are certain GD&T symbols what have been used among all the 5 categories of GD&T symbols over here. So identify, on the extreme left corner they have asked, identify all of the statements below which are true regarding the following drawing. So there are 5 statements over here. We need to identify among these 5 statements which are true. So the first statement is the nominal dimension of the center through hole is 0.315. Nominal dimension of the central through hole is 0.035. 0.0315. Next, the maximum material condition for the overall height of the structure is 1.750. 1.750. And third is the least material condition for the 8 unique through holes on the base of the structure is 0.210. And the fourth point is the least material condition for the overall base diameter is 2.75 inch. And the last, the datum A is called out as the bottom surface of the base. Datum A is called as the bottom surface of the base. So among these 5 statements we need to tell which is true with this particular drawing. Now, coming back to the first statement. The nominal dimension of the central through hole is 0.315. Nominal dimension means basic size or the basic dimension of the central through hole is 0.315. Whether we need to state it is true or false. So just look at the dimension of the central hole. Here it is not, they are not mentioned, but here they are mentioned. That is, this is the central hole, isn't it? And the dimension is diameter 0.315 with the tolerance they have mentioned, and with the GD&T also they have mentioned. But the nominal dimension is basic size, which is 0.315. Hence it is correct. Second, the maximum material condition for the overall height of the structure is 1.755 inch. The maximum material condition for the overall height of the structure is 1.755 inch. The maximum height is represented over here, and it is given as 1.750 plus or minus 0.005. So it is nothing but what? A shaft or a hole? A shaft. And for the shaft, the maximum material condition is the upper limit, and the upper limit for 1.750 is 1.75 plus 0.005. It will become as 1.755, which is mentioned over here, hence it is true. The least material condition for the 8 unique through holes on the base of the structure is 0.210 inch. That is, the least material condition for the 8 unique through holes on the base of the structure is 0.210. The 8 holes on the base of the structure are these holes, and the dimension of these holes they are mentioned as so just wait, I am not getting this. Now I can say this. Okay. The 8 base hole is given as material condition for the overall structure base diameter is 2.75 inch. 2.75 inch. The least material condition for the overall base structure. The least, sorry, we are talking about the third point, right? The least material condition for the 8 unique through holes on the base structure is 0.210. So these are the 8 hole structures, and the dimensions are given as diameter 0.210 plus 0.005 minus 0.002. What is the least material condition for the hole? The least material condition for the hole is lower limit. Upper limit. For shafts, what is the maximum material condition? Upper limit. And for the shaft, what is the lower material condition? Is the lower limit. And for the hole, what is the maximum material condition? Is the lower limit. And what is the lower material condition? Is the maximum limit. Here I have asked the least material condition or the lower material condition is nothing but the upper limit. Hence the upper limit for the shaft is plus 0.005, and the overall dimension will become as 0.215. But they have mentioned it wrong. Hence this statement is wrong. The third statement is wrong. The least material condition for the overall base diameter is 2.75 inch. Overall base diameter is mentioned as 2.75. The least material condition is 2.75 inch. Whether it is true or false, because we have not removed any material, it is looks like a shaft. Hence for the shaft, the upper material condition is the, or maximum material condition is the upper limit, and the least material condition is the lower limit. If you look at that, it is 0.275 plus or minus 0.2, isn't it? And this is a typical shaft. Hence maximum material condition is, or maximum material limit we can say, material limit is the upper limit, that is plus 0.2, and lower material condition or lower material limit or lower material condition is 0.275 minus 0.2 plus or minus 0.02, sir. It is 0.02. Okay. The least material condition for the overall base diameter is 2.0.2. It is 2.75. Sorry, yeah. It is 2.75. So it is 2.75. It will become as 2.77. Again it is 2.75. It will become 2.73. The least material condition for the overall base diameter is 2.75, but here what I have calculated become as 2.73, hence the statement is wrong. I mentioned it wrongly. The fourth point is wrong. So here in this condition, first was correct, second was correct, third was wrong, fourth was wrong, and data ME is called out as the bottom surface of the base. Yes. This is the bottom surface of the base and it is called as data ME, that is